All right, today we're going to take a look at section 5.2. It's titled Multiplication and Division of Integers. And although we don't have the chips with us, I'm sure you guys can imagine what it would be like if you did. So we're going to take a look, first of all, at the chips model. This requires a little bit more explanation than the other ones did. And the language can apply in either order. So I'm going to start with the -4. And that negative is going to mean that I remove something. If there was a positive, it would mean I'd add something. Sound good? And it's going to be removing 4 groups. That's what my 4 is going to represent. There's 4 groups. Over here, it tells me what I'm removing, the 4 groups of. There are 4 groups of 3 negative chips. So you might be thinking, well, what if I want to remove 3 groups of 4 negative chips? Go for it. It doesn't matter. So you can switch the language that I've written on the 2 pieces to do that interchangeably. It doesn't make any difference. It'll still work. Just pick one of them to talk about the number of groups and whether you're adding or removing. One of them to talk about the number of chips in each group, whether it's positive or negative. So far, so good? Okay. So on this one, our image is that we're going to be removing 4 groups of 3 negative chips. So if I start with a circle, and there's nothing in it, then it has a value of 0, correct? Okay, so this circle, from this circle, I want to remove 4 groups of 3 negative chips. But that means there's got to be 4 groups of 3 negative chips within there to remove. And we saw this happen when we did subtraction. Remember, when there wasn't anything negative to remove, I inserted 0 pairs until I was able to actually remove what I was supposed to be removing. So what we're going to do is we're going to remove those groups by first inserting enough to have those pieces there to remove. So I'm going to start out, let me see my 2 colors set up. So we'll do the the red and the yellow, since we had chips for that and you have that imagery. But again, any color will work. So we're going to put in, that's a square, how about a circle? Groups in pairs, so that's 0 still, right? You can put them in groups enough, whatever. So you've got 1, 2, 3, 4. Here's 1, 2, 3, 4. Whatever you're putting them in, they have to be in those groups. 1, 2, 3, 4. 1, 2, 3, 4. I need 4 groups of 3. So I've got almost enough. I think I need a couple more. So here's 2 more here and, 2 more here. So I need 4 groups of 3. So this is a group of 3 that I will remove. So they're removing those 3 negatives. There's a group of 3. So that's 2 groups of 3. Oh, did I end up with too many? I did. Okay. Hang on, that looks weird. How about I erase that one? There's my number. So then there's another group of 3 that I'm removing and another group of 3 that I'm removing. If you put them in 0 pairs in groups of 3, it might be easier. I was just doing it a little haphazardly. So I've removed 4 groups of -3, and what remains? Yeah, 12 positives. So I have my circle remains, and it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 positives left in the circle after I've done my removing. So the answer is positive 12. So my circle needs to have a 0 value. Okay, I have nothing in my circle to start with. This language says that I'm supposed to be removing 4 groups of 3 negative chips, and in order to have 4 groups of 3 negative chips, they have to be in my circle. But I can't just put them in my circle, or that would make my circle equal to -12. So I've put them in 0 pairs to keep my circle's value equal to the number 0. And then I'm able to remove what's not there, or what's there at that point. The same thing happened kind of when we did subtraction. We started with a 0, and then it said 5. Our example was 5, so I put 5 in, and then it said remove 3 negatives. Well, there weren't 3 negatives to remove, so I added groups of positives and negatives in, 0 pairs in, until there's 3 negatives to remove. So the same thing's happening here. I start with 0, and I need to remove things, so I'm removing 4 pairs of 3 negatives. Pairs is not the right word, 4 groups of 3 negatives. The charged fields model, as you've seen before, looks virtually the same as the CHIPS model. It's just that it uses pluses and minuses instead of the colored chips. So you have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. This circle is still 0. I'm trying to now remove, that's the negative, 4 groups of 3 negatives. So I currently have 2 groups of 3 negatives here. Here's group 1 and here's group 2. So I need to do the same thing again because I need 4 groups. So here's a group of 3, here's a group of 3, and I'm removing. So I remove my 4 groups of 3 negatives, and the result is that I have what? 12 positives, right? So I have the result is 12, just like before.
Okay, I don't know why I'm not grasping. Why did we put 6 positives and 6 negatives as our first step if 6 isn't a number that we have up there?
I didn't. I put them in 0 pairs. I was just not trying to add them one at a time because I was going to have to draw a bunch of them.
Okay, got it.
Yeah, so it has nothing to do with the 6. I was just putting them in some sense you could say that I was putting them in group, let's change my color. There's a group of 3, here's a group of 3, here's a group of 3, and here's a group of 3.
Got it.
I just did them in sort of in doubles. Yeah. Okay. Go to the next one, number line model. So all these models are a little weird when it comes to multiplication, not going to lie. So on this one, the context for our positives and the negatives are like this. This negative is to move left, and we should probably be okay with that. We've used that idea before, right? The idea of the negative meaning moving left. And this is going to be moving left 4 at a time. Because it's almost like you're skip counting by 4s. Okay, skip counting by 4s. And then the second part to the number 3 here is the part that feels awkward as we're describing it. When we come to the word problem that you see in your group work for this section, it will actually make a lot of sense at that particular point, but it looks a little bit funny right now. So this one's at a time starting three ago. So put your favorite unit after it. 3 minutes ago, 3 hours ago, 3 days ago, I don't care, but 3 something ago. Okay, so I'll use hours just so I have a context and it makes more sense to write it down. So over here when we were looking at our charged fields model and the chip model, we started with 0, right? And we put things in so that we could actually remove stuff. On the number line model, our goal is to end at 0. Okay? So we're going to draw our number line. There it goes. And here's 0. Actually, let me just put a hash mark there for a moment. So we're starting and we're ending somewhere. I don't really care where you end up and start right now. Just make a mark for it. It says that we're supposed to move left 4 at a time. So this would be 1, 2, 3, 4. So if I jump here, this is 4 at a time, and I'm moving left. So far, so good? Cool. And then I need to do it again, 2, 3, 4. So here's again. And then I do it one more time, 1, 2, 3, 4. And I'm doing it 3 times because it's multiplication by 3. So the idea here is that I'm going this far in 1 hour. So imagine it was like a car driving or you running or something like that. So you're moving in a specific direction 4 miles per hour. That's actually a decent walking speed. So we can use walking or running as an example there. So you're moving in that direction 4 every hour. And you do this for 3 hours. Okay? We end at the number 0. That's our goal. And the question was, or the answer, rather, to the question is, where did we start? And we had to start at 12 for that to happen. So it's like 3 hours in the past. So this ago, I didn't clarify that. Let me do that. This 3 hours ago is telling you it happened in the past. So the question is, where did you start now? What was it when you started? The example in your, I think it's your group work. I don't think it's homework. I'm pretty sure it's group work, so we won't get to it today, but you'll get to it on Monday. Talks about enrollment at a school. And it talks about how the enrollment has been declining. I'm going to make up something, 25 students a year. And the question was, what was it 3 years ago? Do you see how the past tense makes you go backward in time? So while it's been sequentially moving downward by 25 every year, or whatever their number is, their question is what happened, where did it start from? Where was it in the past? So this was what's going on in this particular type of a modeling. Okay, we have a few other things in multiplication to take a look at, and then we will, a couple more anyway, and then we will push pause for today. So some integer multiplication details or properties. So if A and B are integers and A is negative and B is negative and you multiply them like this, then this is the same thing as the absolute value of A and the absolute value of B, if they're both negative. The second line talks about what happens if one number is negative and one number is positive. So if one number is negative and one number is positive in either order and you multiply them, you actually get the opposite of the absolute value of A and the absolute value of B. Oh, that should have gone down the next line. I didn't see my then. The idea that they're using here with these absolute values is the, come on, move on over here, little absolute value symbol. I lost you. Is that if we're thinking about the absolute value of A and the absolute value of B, then we're working with positive numbers already, okay? So if you have -5 and you take the absolute value, you get +5, yes? So as long as you are looking at the numerical value and not its sign, that's the same thing as looking at the absolute value. Well, we know how to multiply with those kinds of numbers. That was chapter 3. We've already talked about that. So this piece is the stuff that we did in chapter 3. It's just multiplication of positive numbers. And if both the numbers were negative, then we're done. But if one of the numbers is actually positive and one of them is negative, then we end up getting a negative of that answer when we're done. Okay, so that's all this is saying in terms of what we've seen before. Now, just like we did in the last section where we did properties, we've got properties, once again, this is our last time, properties of integer multiplication. So if we have integers A, B, and C, there's a closure property, okay? The closure property says that if you multiply A and B together, that this is, well, they've got words, a unique integer. Right, so integer times integer is an integer. And again, we saw that happen with whole numbers. That's not a new idea. It's just extended to the integer system. And I know sometimes it's worth repeating that this closure property happens a lot, but it doesn't always happen. So you guys gave an example in your test. Most of you got it finished to that point of an exact case where it didn't happen. Right, where you gave me an example of something that was closed under multiplication. It was odd numbers. Most of you chose odd numbers. But odd numbers are not closed under addition because you do an odd number plus an odd number and you don't get an odd number. So this is unique to this system. This is an integer property, just like it was a whole number property. It doesn't happen for everything. Commutative talks about order of things. Commutative works for addition and multiplication, typically speaking, and it works again for multiplication here. A times B is equal to B times A. And aren't we glad that it is? Can you imagine learning your flashcards and your multiplication tables back in 3rd grade or whenever you learned them if it wasn't commutative? Whew, would have been much harder. So we've got the commutative property, the order doesn't matter. The associative property we have as well. So if we multiply A and B together first and then multiply it by C, keeping the order the same, it's the same thing as multiplying B and C together first in those parentheses and then multiplying by A. We had that property before. Any questions about any of those? Okay. Our last three properties are the identity, distributive, and zero property. So the identity property, again, this came up on your last test, works just like it did for whole numbers. The number 1 is the identity element. And it works because 1 times A equals A times 1 equals A. It is a number we multiply by, and it doesn't change the value of what we're working with. So it isn't just that it's commutative, although that matters. It's that the result of 1 times A and A times 1 is the same result as it started with, A. The distributive property talks about how we combine addition and subtraction with multiplication. So if we have A times B plus C, and it's actually plus or minus, just so you know that will work. So if you A times B plus or minus C, then this is the same as AB plus or minus AC. And the order of the multiplication doesn't matter. If the A's in front, fabulous. If the A's behind, equally fabulous. So B plus or minus C times A, I would just have BA, or you could even write it with AB plus or minus CA, or written AC. So you see people draw arrows through a lot. I know I do when I'm describing it. I do like this. So I'm distributing my value A, in that case, through both of them. And the last one is the special number 0. So 0 is the unique integer. Such that A times 0 or 0 times A is equal to 0. Notice how that's different than D, right? On the 0 property, it's zeros everywhere. On the identity property, it's A's everywhere. Okay, we're going to do example 4, and then we're going to pause for today. So example 4, I'm going to give you just a minute to figure out what property you think is at play in there. So you've got 6 properties above. Your goal is to write down a property for each of the letters A through D. And then once you have, turn to a neighbor and just compare. See if you have the same things, or if they're different, if you can reconcile between yourselves which one it should be. And then we'll come back together. Okay, let's make sure that we all have the same thing. So what property do you believe is at play in number A, letter A?
Closure?
Yeah, that's the closure property. It's written a little differently than I wrote the phrasing out. But if you'll remember, this symbol means is an element of. Do you guys remember that? Yeah, it's going to come back up. And we're letting I represent the integers. So it's an element of the integers when it multiplies 2 values together. So yes, indeed, it's the closure property. How about B? Yep, that's the 0 property. All right, property after each of them, or at least prop. How about C? That is the distributive property. And how about D? Commutative, very good. Okay, so we'll pause on 5.2 for today and turn your attention to looking at 5.1 on your group work.